Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about how we can linearize the equations of motion and find an equilibrium position. Let's jump right in. The equations of motion that we found with the principle of virtual work or the Lagrange equations are nonlinear. That means that they depend on cosine, on sine, they have exponential function, and so forth. And to solve these equations after getting them, which is already a difficult step in the first place, solving them is very, very difficult and very, very annoying. But if we have a system that has small displacements close to some equilibrium position, so it is oscillating, we can do vibration analysis, and that will be the main topic of this videos. So if we do vibration analysis, we get first linearized equations of motion, and then we evaluate the stability. So our goal is get linearized equations and evaluate stability. Is it stable? Is it not? This stability topic will be in the next video. We are now just focused on any equilibrium position and the linearized equations of motion. So the first step that we have to do is, of course, finding an equilibrium position. And the definition of an equilibrium position is when our generalized coordinates are constant, so they are not changing. That doesn't mean they are zero. It means that they are not changing. So for example, that q double dot is zero, q dot is also zero, and q's are at some equilibrium position. And again, q equilibrium is not zero because we can have, for example, Rehonomic constraints. I have an example right here. So we have a mass that is spun around, attached with a spring, and the centrifugal forces are pulling the mass away from the center, but the spring forces are pushing it back. So there will be some equilibrium where x will have some length, but it will not be zero. But the change of x and the change of x, so x dot and x double dot, they are zero. So they're not, x itself is not changing it at a constant. And that point we refer to as a equilibrium position. So we have those equations of motion that can depend on q dot, and q double dot. And we have, of course, n of those equations, because if we have n degrees of freedom, we have n equations. And one of those equations, for example, that we got from the Lagrange equations is this part. So we have kinetic energy. In this part, we have potential energy here, and we have non-conservative forces. So we have n equations for n degrees of freedom. And now our goal is to find the equilibrium configuration. We don't know if it's stable or not stable. We just have to find it. And we do that by setting q double dot to zero, q dot to zero, and the q's will now become our q equilibrium. This whole term, or all the functions, will be zero. And this is how we can find our q equilibrium. That's how we find it. Maybe difficult to understand at first, but if we look at an example, it will be very, very easy. So here we have one equation of motion for our pendulum. We have 1 degree of freedom, and that is the angle theta. So we have one equation of motion. We set q double dot and q dot, in this case, theta double dot and theta dot to zero. So this will be zero. We have no theta dot, and we set our leftover theta, in this case, to theta equilibrium. And now we just need to find this theta equilibrium, and it will give us two results. So we have either 0 or we have pi. So if we draw the equilibrium configuration, we have one where, sorry, this is wrong. The angle is, this angle is 0. Maybe it's difficult to understand. We have an angle 0, I just do it like that. And we have a upside down position where we have this angle being pi. So One time it's pointing down, the other time the pendulum is pointing up. What position is stable, what position is unstable? We already know it, but we can't express it mathematically so far. But this will be in another video. So now that we found the equilibrium position, we want to linearize around that position because we have a sign here, and these difficult part, those complex parts we need to get rid of. So we have those nonlinear parts like sine, and we want to get rid of them. So we have a equilibrium position, and now we do a Taylor expansion. So we get our equation of motion, and we have this point, so the starting point, which is 0 by definition, because that's how we got it. So we have 0. And then we do a partial derivative of our equations of motions with q dot, evaluated at equilibrium times q dot, plus partial derivative with here we have q double dot, here we have q dot, and here we have df dq. So a simple partial derivative at equilibrium again times q. So these parts will give us matrices. The M matrix, called the mass matrix, D matrix, damping matrix, and K matrix is the stiffness matrix. So how do we get these matrices? So if we have a value at position Rs, we get the R equation of motion and partially derive it with our degree of freedom S. So in this case, for example, we take the first equation of motion and derive it with our first generalized coordinate. Then we take the second degree equation of motion and again derive it with our first degree of freedom. Then we do this for the second equation, for the second degree of freedom. So we take the first equation of motion and get the second degree of freedom. Then again, we get the second equation of motion and second degree of freedom. So we have 1, 1 here, 1, 2, 2, 1, and 2, 2. So this is how we get a matrix. So we get a n times n matrix because we have n degrees of freedom and n equations. So let's look at an example so it's easier to understand. Step number 1 is to get the equilibrium position. We do that by setting our q double dots to 0, q dots to 0, and q is our q equilibrium. So we have, this is our q, so x double dot is 0, theta double dot is 0, x dot is 0, and theta dot is 0. X dot double dot, this is 0. Here we have a double dot, this is also 0. Here we have a single dot, this is also 0. X double dot is gone, theta double dot is gone, and we are left with this and this part. So this is what we are left with. And based on that, we can now find x equilibrium and theta equilibrium. For x, we have a equilibrium at 0, and for theta, we have one at 0 and one at pi. And again, we have, if we draw it, we have the mass that is not moving, so it's right at the origin. We have one time the pendulum is downwards, and the other time the pendulum is pointing upwards. We again already have an intuition which position is stable and which position is not stable, but we will cover that in another video. So now the goal is, after we found the equilibrium position, we can now linearize around that position. We want to first get the mass matrix, and we get the mass matrix by deriving with our q double dots. So let's see where we have q double dots. We have q double dots right here. That's where we get this one from. Then we take the second equation, look at the first degree of freedom. This is again our x. So we have this part here. A theta double dot is present right here. So this is where that's coming from. And a theta double dot in the second equation is this one. And now we have to evaluate it at the equilibrium position. So the theta and the x, we don't have an x here, will be at a equilibrium position, and we chose this one, so 0, 0. Cosine 0 is 1, so we're only left with that. For the damping matrix, we have to do a partial derivative with our Q. So let's look where we have a Q dot. The only Q dot that we have is here. If we do a partial derivative, we get this part with a 2 in front and only one theta dot left over. But because we are setting the Q dots and Q double dots and Q dots to 0, this part will be gone because one Q dot is still left over. So we have 0 for all entries. The stiffness matrix, we get that by partially deriving with our Q's. So we see where we have some Q's, we have one Q there, so this is the X. Nothing in the second equations regarding the X. We have no theta in the first equation, but we have one theta in the second equation, so this is where this is coming from. Evaluated again at the equilibrium position, this will be our stiffness matrix. So if we linearize around this position, we get a mass matrix and a stiffness matrix. We have no damping matrix, and we have no sine and no cosine left. So these matrices, the M matrix and the K matrix, are special or constant for each equilibrium position. So if we found them, they are only valid for this specific equilibrium position. I hope this video gave you a small or a better understanding how we get the linearized equation of motion and how we get a equilibrium position. So this is the most important part. Set Q double dot to 0 and Q dot to 0, and you will get the Q equilibrium. And then you just do partial derivatives of your equation of motion to get the M, D, and K matrix. After that, you just slap them together and you get your linearized equation of motion for one equilibrium position. Thank you very much for your attention. If you have any comments, ask them in the questions down below. I will do my best to answer them, and I'll see you next time.